So we're doing the problem session today, and we kind of wrapped up the lecture more or less yesterday, but we didn't quite cover the
double voltage problem.
Yeah, when you have two switches. And that's going to be on one of the homework problems. So let me just go to that slide here. That's slide 19. And so this is where you've got one voltage source coming on at time 0, the other one coming on at 1 second. And this, when you actually look at assignment 9, is going to be similar to what happens in problem. It's not on our handout. It's not one of the ones we're doing in class today. But we could take a look at it maybe later if we finish the first 4. This one here, where you have a current source coming on at t0, and then another current source coming on at t equals 1. So with the solutions, I was kind of going over I don't know, I mean, we could finish this if you want, so you have it on your notes. You want to do that? Or I can just go over it.
Can we start from scratch on it?
Do you have your notes?
Yeah, I have, yeah.
Because we got like halfway through it yesterday. You want to finish it, or what do you mean by start from scratch?
Well, yeah, when we started it, though, a lot of it was like, because we were rushed at the end, you know what I mean?
Yeah. You want to do that?
Yeah, I would like to just work it out.
Would you like to work it out by looking at what I have written already, or would you like me to erase all this and start all over?
I would like you to erase it and start over. I like it when you talk through problems step by step.
Okay. Gonna be that way about it, huh?
I guess it was an example.
It is going to eat into your problem session, though. That's all I'm concerned about.
Okay. You said there's no op-amps on the homework, right? For this?
No, that is correct.
All right. I mean, maybe just since you kind of went over the theory behind it yesterday, we could just work through the problem like it's a problem, if that makes sense.
Yeah, let's do that. That's a good idea, because then it's continuous and
yeah,
stuff.
Instead of reteaching it, just like, okay, here's a new problem.
Yeah. It's a good conceptual thing to see what's sort of really happening with these circuits. And kind of like what we did, like what we did in the lab. When we did in the lab, when we pressed the switch and we charged the capacitor. We charged the capacitor, but we didn't let it go all the way, and then we let go of the switch and it discharged from where it started. That kind of thing, where you have two switching events going on. That's the kind of situation that we have here. So we have to squeeze this all into one slide, although I guess we could always make a new one. So the thing is, this one turns on at 1 second. And this one turns on at t equals 0. So that second source, or the source on the left there, is going to be off at the beginning at t equals 0. And so with the first circuit that we solve, we have that thing turned off. And so for 0 to 1, the circuit is going to be like this. Oops. Where this is going to be 1 volt. Why are you doing this? And we're going to try to solve for the current going through that 2 Henry inductor, right? So the solution is going to be, you know, I of t is going to equal I infinity plus I0 minus I infinity e to the minus t over tau. And our initial condition for I0 equals 0 because that source was off. This source, you know, this equals 0 for t less than 0 and 1 for t greater than 0. So in the steady state, you know, long times pass. These things, I mean, these have been off for a long time. There's no initial current flowing through that inductor. So I0 is 0. That's because of the initial condition. IL0 minus equals IL0 plus. All this stuff, you know, maybe we should just sort of skip over that kind of stuff because we've been doing that a lot. So tau is going to equal L over R Thevenin, which, as we saw, is 2 Henrys over, and then what that inductor sees when what I'm doing to make this thing go flip all the time. I'm gonna figure that out. Pissing me off, man. Because you know I'm wearing kind of a nylon shirt, which is, you know, full of static electricity. It's probably what's happening. Yeah, be a good final project for circuits.
Figure out what the thing is. My final project is rubber gloves.
Right. Metal shield. Probably need a grounding strap. That's what I should bring in. So the Thevenin equivalent. Okay, so when basically, you know, I have a voltage source. So whether they're off or on, they're going to be off when you're finding the Thevenin equivalent, and it's just 3 in parallel with 6 for that, right? So it's 3 parallel with 6 here. Everyone cool with that? So that's just 2 over 2 or 1 second. And the I infinity is sort of the asymptote, assuming the second source never came on. Just did it again. Okay, fine. Yeah, am I touching a touchpad? It's not consistent. And in the steady state, the inductor has become a short circuit. And so in the steady state, when you have that 1 volt source there, essentially what you've got is where that short, which is the inductor, is bypassing the 3 ohm resistor. Mm-hmm. So the current going through here is just going to be 1 volt over 6, right? 1/6 amps. So that means our solution for 0 less than t less than 1 is that I of t equals 1/6 minus 1/6 e to the minus t over 1. And that's kind of where we left it last time.
So what was our I sub 0? We said it was 0?
Yeah, I sub 0 is 0. And you reason that because both of those sources are off for t less than 0.
Okay.
So there's no source on for infinity of time before the switch turns it on, then there's no energy in that inductor. Right. So the question is, what's happening now for t greater than 1 second? Well, for t greater than 1 second, you've got this other circuit now. I mean, you've got this other source that's come on. Wish I could program my pen to stamp out circuit diagrams.
Just have like a clipboard on there with multiple entries.
Yeah, just make it show up. And we could treat this like a regular first order circuit, except what's confusing about it is that this, the switch is coming on at t equals 1 second. So this is where I was saying, well, what you want to do is, to make this work out so you don't screw anything up, we're going to make a t prime variable, which is going to equal t minus 1. And then we can reference everything to this t prime variable in this domain, and then adjust our time variable later when we get everything all straightened out.
So 1 second, both these sources are on?
Yes.
So now we're solving for I of t prime.
So yeah, so we're just going to solve for I of t prime. And in this case, our I0 is the initial condition. But we're not in the steady state at this point, right? We're actually in the middle of this exponential curve from the first solution, right? Mm-hmm. So we don't use any of that steady state stuff anymore, but what we do is we find that IL of t prime equals 0 plus has to still be the same as IL of t prime equals 0 minus, which equals I L of t equals 1. Using our last formula, right? We plug in 1 in the last formula that we just solved, figure out where we're at that point, because that's going to be our initial value of I for the second source coming on.
So it's IO is I what minus IL of the t-prime? Your last line?
It's IL of t equals 1.
Or the second to last line? Is it next to
IL of t prime equals 0 minus?
Right after the IO in the colon. Initial condition. Oh.
Initial condition, yeah.
Oh, okay.
IO is the initial condition. It's the initial condition for t prime equals 0. 0 plus. This is a 0 plus, not a prime. So our I0 then is going to equal, it's going to equal just that formula. It's going to equal 1/6 minus 1/6 e to the minus 1. And that's going to equal 0.105. So that's where we got to when we, right when the second source turned on. That makes sense. So the tau in this time domain, thank you very much, is L over R Thevenin.
Shouldn't it be the same tau?
Yep, it's the same.
Okay.
Same R Thevenin, same inductance. I infinity will not be the same though. This is again our steady state condition at infinity where the inductor again equals a short circuit. And in this case, you know, you're going to want to convince yourself, you'll probably want to draw that circuit again and figure out what is the current going through that short that the inductor has become. Could be, let's see, could be, you know, this is a good case for superposition. Remember superposition?
So if we turn one off.
Yeah, you turn one off, turn one on. This is kind of what we're doing anyway, right?
Well, we already have one.
We already found one of them, right? So yeah, so I infinity. Let's just write, thank you, superposition here.
Plus whatever the other one is.
Yeah, what do you think the other one's going to be?
Also 1/6?
Nope.
No? Oh, no, it's going to be 1/3.
Yeah. You turn off the other source, right? Then you're shorting out, then the inductor's shorting out the right source, and then it's just, or the 6 ohm resistor, and then it's just the 1 volts over 3 ohms, right? So it's 1/6 plus 1/3. And that equals a half an amp. Here. And yeah, so for t prime greater than 0, I of t prime equals 1/2 plus 0.105 minus a half. That's the I0 minus I infinity. E to the minus t, I don't have any room for that, e to the minus t prime over 1. And then now that we've been careful about this, we can put back the real value of t prime. T prime equals t minus 1, so we can throw that in there.
On your e, was that e to the minus t or t prime?
It's e to the minus t prime still.
Okay.
We're still in t prime. So now we want to actually put this back into I of t, which we're going to just say, okay, so that means I of t is going to equal 1/2 plus 0.105. And this is going to be, I put an arrow here, e to the minus t minus 1 over 1. So that's how you are going to do this problem on the assignment number 47, only it's a capacitor. Same idea. Okay, so are you ready to grab some markers and get active here and solve the 4 problems we have? We've got 6 people here, so double up if you want.
Which problem is this?
It's number 47.
Oh, on the bottom it's 47.
Which problem is what?
Or this one? I didn't have a number on it.
Oh, no, that's not 47. The one that you're going to use, that technique we just did, is number 47.
Oh, okay.
This problem is, what problem is this? Oh, it's 39. It's just, there's 2 parts to 39.
Oh, so we have
It's 39B, yeah.
So we have 3 problems?
Yeah, 3 problems with 1 or 2 parts.
Okay.
Okay, answers for all those, right? Yeah, cool.
Yep.
Okay, so we are going to, oh, I wasn't sharing the screen. I guess no one's here anyway, luckily. Just in case someone shows. No.
I call that number 7.
All right, let's do number 7, Emma.
Yeah, the one mistake I made on that test was like I forgot to carry a minus sign.
That's
my
minor
tangent.
error.
And then the one other mistake was that I forgot a t.
So
I added an extra t.
So it's just -1 2 times.
Yeah.
Oh, nice.
Yeah.
Good.
Because like I was supposed to like multiply 6 times the my second y prime or y particle prime, and then but I accidentally added a t up there even though it wasn't there.
Okay. How'd you feel about the one yesterday? Whatever VO is going to be whatever its voltage is like at this moment, right before t equals 0. So at this circuit, before the switch.
Okay.
So
right.
Yeah, so we just find the voltage like as is the way you drew it.
Okay.
Did it, wait, is there a V0 given to you for that one?
No, we're supposed to find V0.
So, assuming it's been in position for a long, oh, it's been in that position, wait.
Yeah.
But wait. Let me pull that up here. This is number 7? So in this circuit, it's been in position A for a long time. It's moved to position B, 2, 0, 1, B, 0, 2. You know, what's interesting is they don't really... Oh yeah, your capacitor is seeing the voltage, right?
Yeah.
There you go. Okay. I thought it was actually floating, but it's not.
Yeah, so in the capacitor, the voltage cannot jump, right? So
Right.
it should be the same thing even after.
After you're switching it, momentarily it's going to be the same value.
Yeah, so we'll find the first voltage, then we'll find the second voltage, and we'll find the tau, and then bada bing, bada boom.
Yep, yep.
Okay, so let's find the voltage this way.
Yeah.
So we have.
I need to say bada bing, bada boom.
You
more.
do like that.
Okay.
All right,
So
so
we have this resistor, and
we're ignoring that resistor.
yeah.
So let's draw a new circuit. So that's going to become, it's in the steady state, so that's going to be an open circuit. Where the VO is. Yeah, so let's draw it. Just draw like a. All right, so we want to find the voltage there. So whatever our voltage is here, I say we do nodal analysis, because that seems easy.
And thereby avoiding one of the most simple formulas you could ever use in circuits.
So you want to find the voltage across the 20K, okay? So
Hey, we should probably use the voltage divider.
Yeah, that would be.
I think that would be good. Tom doesn't like taking the scenic route.
Just get to the point.
is that right?
The voltage divider formula?
Yeah.
Oh, that's just
12
6.
times. No, wait, isn't that 40?
Oh,
That's 40.
right there.
Okay.
Yeah.
That's 40.
So 2/6 is 1/3 times 12. That should be 4. Oh,
4 over 6, right? 2/3 of 12. Yeah.
okay. Should be
That's better.
8. So that's our. So
You guys working on 11?
8. Now let's find tau. All right.
So this is a.
It's going to be the capacitant. Yeah.
I0.
It's the R-Thevenin.
Are you doing a mesh analysis?
At which point though? Was it
That's
before or
cool.
after the
Fine
switch?
I0.
So after the switch? Yeah, let's go.
Okay.
Let's go with it after the switch. So that means we'll ignore this resistor.
Uh-huh.
Where? Don't get the answer. Just solve it.
1.41 amps.
It's like a super simple math problem. No. Yeah.
Okay. Our Thevenin is.
So our Thevenin should just be these two resistors, right? The 20 and the 20. You okay, buddy? You gonna wash your eye out real quick?
Okay, cool.
So the 20, those two 20s are parallel, aren't they?
Yeah.
So 1.41. It's 10.
You got the same answer as Robert. So how did you guys do that? 24 over.
So that gives us 10 as our element, so it should be
Because this
equal
gives
to
you
our
the, well, this doesn't
right?
really equal it. This equals like 4 points. So
No,
then you
it's
do
millimoles
current
times kiloohms, so
divider.
it's just going to
Then
be.
you-
Okay, so you actually did a couple steps
So
here.
yeah, this should actually equal.
10 times 0.2.
Oh, no, it's kiloohms times millifarads.
Yeah, that's good. And then you're doing the current divider formula.
Current
Good.
divider.
That's cool.
You can do
Nice.
0.0002 times 10,000, but 20 seconds. 20 seconds. Smell
And then do 4.
ints, as I call it. It's the voltage after the switch.
Nice.
So let's redraw that.
That's your I0 then. Cool. Awesome.
Into point B.
Okay. Amara, how are you
We
doing?
got the right towel.
You're doing 39A?
Yeah.
Is that A? Okay. Okay.
So, and that's 20 ohm, so two 20 ohm resistors. And those are in parallel, so.
And the switch is,
so we could just do voltage
Is
divider.
being opened at 0?
Yeah.
Okay.
So it should be
Sounds
6,
good.
right? Yep, now let's put it together. So the formula should be
So you're finding your
V infinity. So
initial
it's- so
capacitor
VFT
voltage.
Oh yeah, because these sources
VFT is equal to 6.
And
6. V infinity plus VO, which is 8.
E to the,
No, not yet, Doug.
really?
No, it's plus VO minus V infinity times the E.
Plus, okay, wait. So it's B infinity plus VO.
No, so it should be like this. The formula is V of T is going to be equal to V infinity plus parentheses VO minus V infinity
E to the minus T
E
over
to the
top.
minus T over.
And your VO is A and your V infinity is 6.
So it should be 2. So gratitude.
Okay, fine.
There. E to the minus T over 20, which is the answer.
Nice.
Nice.
That infinity
Good.
though.
Let's connect them. It's an open infinity.
A double O.
Whenever I try to do the sideways 8, it always looks weird. I'm not good at it. Like,
Do you do the regular A like this too?
no, regular 8 I do like that, but whenever I try and do like a square root infinity, it always looks like
Okay. You, how's our Thevenin going?
I'm not sure how to find it. Towards that.
Yeah. So when you find our Thevenin, you can turn off the voltage source by making it short. And well, actually,
It doesn't matter.
wait, the switch is going to be open, right?
So it's just these two. Okay.
Yeah. It's just those in series. It's the resistance seen by the inductor. And it's helpful to redraw the circuit, with all that stuff out here. But like you're right, this goes away because the switch opens,
So it'd just be these two.
and the resistance from A to B when you remove the inductor,
All right.
which is just the sum of those two.
Yeah.
You got that? Your tau was 4 over 12.
When the
Yeah, there you go.
switch is open, so it's just this right.
Mm-hmm. Yep.
Okay.
Cool. Nice. Yep, that's how it works. And Emery, have any questions or?
No, I just forgot something. And then I just remembered.
Yeah, if it's not source free, then it's going to be the longer formula, right? So there's still 39B. Someone could try that.
We're gonna do 39B right now.
Are you doing 39B? Good. Awesome. Okay. Looks good.
Now you have to do the R cabinet.
And then, yeah, you can find after the switch opens, what is the resistance seen by the resistance seen by the capacitor?
Those in four.
Just going to be 4 ohms, yeah,
Yeah.
because that 1 ohm resistor is taken out of the circuit basically.
Tom, you got this one, right?
Yep.
Can we erase it?
Sure.
Let's do another one.
Do 39B.
We have to study for this test.
It's not. It seems like it's the same thing over and over.
It is, but it's there's a certain amount of novelty in each circuit.
You just have to be really careful.
And then second order circuits we're doing next week are going to be pretty challenging.
Okay.
Yeah, those are really complicated.
We always up the ante right when I feel like I'm
I
getting
know.
my feet like planted.
Right before a
slip the
test
rug.
too.
What is that? Yeah,
I think it'll be after second order circuits. So. It's
Sure.
week 12. This is we're in week 9, right?
Okay.
Yeah, so actually we're going to do second order circuits, then we're going to do phasers, I think, and then the test.
The angles
Complex
from harmonics.
complex phasers, those you got those in
Yeah, the
in
angles,
3C.
The angles from harmonics.
Yeah, it's the same thing you get in 3C.
It's where you represent the like
A sinusoid with
with
a complex
angle.
number.
Yeah.
Oh.
That's when we use I to represent a complex number, right?
Yeah.
J. J.
Let's do.
Do they use I in physics?
No, I think they just have it on the vector. They just use the vector.
Yeah, but basically the thing we
Oh yeah, we didn't have a complex number.
Oh, they use complex numbers in physics?
No.
In 3C? Oh,
I
that's
I'm
terrible.
just using vectors and like
Huh.
We go in circle.
Well,
Like
whatever.
We barely,
phasor
actually,
diagrams. That's right.
we barely went over it. It wasn't even on the test.
Yeah. Monster made a big deal.
It's going to be on the next. It's going to be on your test, test 4.
I'm learning more from circuits than I am from physics anyway.
Yeah, I know. It's sad but true.
From the Harnell physics book. That's what I'm.
Oh, right.
Let's do. Well, she's doing 39, so I don't want to.
She's doing 39A. You can do 39B.
Let's do 39B.
Or if you want to tackle that one that has those 2 sources in it from the homework, I could pull that up on the display if you want.
No, yeah, let's do it. Let's do it.
Want to do it?
Yeah, pull it up.
Let me pause this a second.
Just look at my face over there.
This is 39B.
Yeah.
And so what you got so far? You got so you started here with t less than 0.
Yeah. So you have
And you have the, what is this thing here? The switch is open and then it closes, right?
it closes it.
And you got 2 sources. So you got to find that initial condition. And, right, you've got a open circuit here where the capacitor is. And you got the 12 volt source, 3 ohms. And then this thing is going to give you basically 8 volts here, right?
We didn't write it
Yep.
down.
And so you got 12 minus 8, so you should have 4 volts for 0. That's good. Yeah. And then for t greater than 0, that switch is closed now,
So
and
do you write it like that? 'Cause
you're finding V infinity. And yeah, I agree. That's going to be an open circuit. You've shorted that thing out, so you basically are ignoring the right side of that circuit,
okay,
right?
so yours is ignoring.
Mm-hmm.
So then
And so then
this is basically just the 12 volts. Then.
no current flowing. It's an open circuit. You got 12 volts there. Yeah.
Okay, so okay.
Yep. And now all I got to find is tau. And so tau, again, is for t greater than 0. Actually, you know, this, to be more accurate, this is sort of as t approaches infinity because you have an open circuit there again. That's, yeah, but anyway, it's the same idea. And the tau is for that circuit.
So
What is the resistance the capacitor is seeing?
it's just 3.
3 ohms, yeah.
Okay.
3 ohms, and it's a 2 farad, so it's 2/3 of a second. It's good. So you got R Thevenin is 4, and tau is 2 times 4, 8 seconds, okay. And then your final value of the capacitor. So the infinity is going to be what?
V infinity?
Yeah, so in other words, once that circuit has opened, once that switch has opened, you can ignore that part. You just got this thing. In the steady state, once everything settles down again, that's going to become an open circuit. What's the voltage going to be across that when this is disconnected?
Across the top open circuit?
Across the capacitor, once it's become an open circuit.
Would it be the 4 volts then?
No. So what's that?
It's 20 volts.
Okay. And when this is an open circuit
How would I find it?
in the steady state again, right? And you know that switch has disconnected that 1 ohm resistor, so that's not really a factor anymore, right? What's the voltage going to be across that open circuit?
20 volts?
Yeah, so that's your V infinity. Okay, so now you construct the solution. And the general formula is V infinity plus parentheses. You might want to just write out the whole formula first, yeah. Plus parentheses. Wait a second. V0 minus V infinity. Or what you're calling V1. But why don't you write a V0? Because, you know, that's good. V infinity plus parentheses. V0 minus V infinity. E to the minus t over tau. And, you know, it's not hard to remember this, but you can also check it, right? Because at t equals 0, this is going to be 1.
Yeah.
So it's going to be V0. And at t equals infinity, that's going to be 0. So this is going to be V infinity. Yeah, that's good. Okay, did you guys make it work here?
We either did it wrong or I think the
There's an
answer
error?
here
Think there's
is
an error there?
wrong. Because we got
And the time constant?
yeah.
What does it say here?
Over 6.
It says
Yeah.
minus t over
I
6.
don't know how we get 6 from that.
Well, let's see. Oh, but you know, you actually removed a short that was also here. Does that matter?
It's supposed to.
Maybe not. Let's see.
Well, isn't the time constant for capacitors different than I think that's for inductors?
Oh wait. Oh yeah. So it's actually. It's
Oh,
actually
did you-
3 times 2? Yeah. Okay.
Did you do? You did C over R. Oh, I did that. I said that. I said 2 over 3, right? That was my mistake. Getting them all mixed up, right? It's RC, yeah.
Yeah.
So it's 2 times 3. So let's fix that here.
That's all right.
Sorry, online people, if you're watching.
Yeah.
Good. Okay.
Okay. That's
Nice.
okay.
So for the answer here, it says 12 minus 8. Would that be
12 minus 8.
wouldn't that be of this
You got
was 12 volts?
You got, so wait a second. So the initial value, well, so the final value, when that thing opens, the final value is going to be 20 volts. Right. I was at 12. Let me see what you guys did. You guys did, Emma, you did this
I
one,
had a
right?
question. I didn't get.
You didn't get the right answer either? Okay, so it looks like there's an error in the answers.
Oh, that's what I have, yeah.
So you got the initial, or the final value was 20 volts, right? And the initial value was 12?
4.
No, 4 volts, right? Yeah. Okay, so, and the time constant was 8, 4 ohms times 2 farads. Yeah, good. So that means, yeah, it's 20 minus, it's 20 plus V0 minus V infinity, which is minus 16. Yeah, I like that. You agree?
Yeah.
Yeah, okay. I'll have to send out a correction there. Thank you. You guys make any headway? You didn't make any progress, and it's we only have 3 minutes to go. Maybe we should give up.
So over here, so when I try to find the voltage at t less than 0 or t equals 0, right? Only this would be activated,
Yeah,
and it would be 6 amps.
so you want to find, initially you want to find the V0 is when they're both off, right? If the t equals 0 minus, that's not turned on yet, and neither is that.
Oh.
And so the V0 is going to be 0. There's no, this is off, that's an open circuit, that's an open circuit. You basically have a capacitor going through these 2 resistors. It's discharge any energy, so V0 is 0.
V0 is 0. Okay.
Yeah. So that's, the one thing is, yeah, you wrote for 0 to 1, but you want to first do it for t less than 0. That's how you find the initial condition.
I see. And, okay. Okay.
So that's V0, and then V final is the V final when only this guy has turned on, right? So you draw the circuit, yeah, that's good, with that one still off. And what's the final value? What's in the steady state when this becomes an open circuit?
Then it would just
What's
be,
the
what's the voltage?
yeah? What's the voltage going to be?
It's going to be, okay.
That's a challenging one, isn't it?
Yeah, well, yeah, it's not.
It's going to be what? What do you have?
It's going to be 6 times 8. 42?
6 times 8
Yeah, 42.
is 48.
48, yes.
Yeah.
48.
Okay. Is it 48 or minus 48?
It'll be minus 48.
What do you say?
Plus 48.
What do you think? Is it plus 48 or minus 48?
Minus 48.
It's the initial value, right? You see this, Danny? What do you think is? Because you got an open circuit here in the steady state, right? You've got 6 amps, 8 ohms. So you're going to have 48 volts. All 6 amps has to go through this 8 ohm resistor. So 48 volts plus minus, right? Which happens to line up with the plus minus of our V, right? So it is going to be plus 48.
Oh, okay. Wow.
So that's the V final. So it's going from 0 to 48, and the time constant is going to be, for the time constant, you turn off the current source. It becomes an open circuit, so that R Thevenin is going to be what?
Okay, so it's just going to be 2 plus 8, so that's going to be 10.
Yep.
10 volts is all
Yep.
7 and 10 times 0.1 is 1. Yeah, 1 second for the
1 second. Mm-hmm. Yeah, we don't have the answers on this one, so we have to be careful, right? So that is, yeah, it's RC, 10 times 0.1 is 1 second. Uh-huh. So that means,
the final equals
48.
48.
And V0 equals 0.
Yeah.
And so the total formula then for that part of the for the first part is going to be V infinity is 48 plus V0 minus infinity. That's going to be negative 48 e to the minus t. Right.
Which is
Just 48 minus 48 e to the minus t.
yeah.
Now, at t equals 1 second, then the second source comes on. and that changes things, right? So at t equals 1 second, you can find, you make a new thing. Okay, for t greater than 1, you're going to make a t prime, which is going to be t minus 1, and the v0 for t in that second domain is going to be when you plug in a 1 here.
Okay.
So 48 minus 48 e to the minus 1. And then you find the final thing, so it's not that hard.
Yeah. Hopefully we'll have some trouble.
No, should be.
Right. Should I erase this?
Yeah, you can erase it. Thank you.